right, this is AP, AB, and BC Calculus. We're doing Unit 6, Section 14, which is Selecting Techniques for Anti-Differentiation. So basically, there is no lesson to Section 14. This video is just a ridiculous amount of practice problems. No examples. I'm going to walk through them, but I suggest that you pause me first and try them and then watch what I do to see if your choices were sensible or if something went awry. It's imperative that as you look at an integral, you learn to triage which problems fit which techniques. The only way to do this is to be exposed to a lot of practice. For many of the problems, I've actually given you two very similar integrals that you can do side by side to see the subtle differences that are hugely important in the choices you make for integration. A quick note, there are 14 practice problems. The last ones, P9 through P14 in this video, are BC only because the BC students have learned 3 integration techniques that are not included in the AB course: parts, partial fractions, and improper integrals. AB students should only work through P1 through P8. BC students should work through P1 through P14, which is all of the problems. So let's go ahead and get into it. All right, so we're going to go ahead and integrate. What we have here is a product, but what I want you to notice is that the x cubed plus 3x is not inside any sort of a power or anything, so I can just go ahead and distribute and then do a simple power rule here for both of these. So I'm going to have a 10x to the 4th plus a 30x squared dx, right? When I integrate, I'm going to up the power by 1 and divide by the new power, right? Up the power by 1, divide by the new power, and then there's my plus c. So I'm going to get a 2x to the 5th plus 10x cubed plus c, and that's it. All right, for the next one, similar situation, right? I'm going to have a much easier time if I recognize that I can distribute this power, right? So I'm going to do a little bit of algebra before I do calc, and it's going to make life a lot easier. So remember that 2 is actually 4 halves, and x to the 1st is actually a 2 halves, right? So when I distribute, I'm going to get that this is an x to the 3 halves, because it's 4 halves minus the 1 half, right? Plus 5x to the 1 half minus a 2x to the negative 1 half, and then a dx. And then I'm just going to use the power rule for all of these. So I'm going to up the power by 1, and then when I divide by 5 halves, I'm just going to go ahead and skip to multiplying by 2/5, right? Up the power by 1, I'm going to get a 3 halves, right? So this is going to be a 3 halves. And then instead of dividing by 2/3, or by 3 halves, I'm going to multiply by 2/3. So I'm going to get a 10 thirds here, because the 5 times the 2/3, right? And then I'm going to up the power by 1, which will be a positive 1 half. And then instead of dividing by a positive 1 half, right, I'm going to times by its reciprocal, times by 2. So I'm going to get a negative 4x to the 1 half plus c. And again, if you needed to see this as x to the 5 halves over 5 halves and then jump to this step, nobody thinks that's cheating, right? Same thing if this was a 5x to the 3 halves divided by 3 halves and then recognize that it becomes this, that's not cheating. Same thing if here you had a 2x to the 1 half divided by 1 half and then cleaned it up, that's not cheating. It's just a lot, it's a lot easier to spot how to deal with those fractions. All right. Here we're looking at u-sub, right? The only function that's inside another function is the sine, because that's a sine of x to the 4th. Sorry, I started to write sine when I meant cosine for the second bit. So it seems pretty likely to me that I'm looking at a u that is sine of x and a du that is conveniently cosine of x dx, meaning du is literally this. So this is the integral of u to the 4th du, which means I'm going to get u to the 5th over 5 plus c. So my answer is sine to the 5th of x all over 5 plus c. If you don't like the over 5, you could also write that as a 1/5 sine to the 5th of x plus c. Same answer. All right. E to the 3x, right? So I have this u here, right? Which means my du is a 3 dx. Now, if you could just do this one in your head, that's a good sign, right? It doesn't mean you're cheating. If you can just look at this and say, wait a sec, that's a 1/3 e to the 3x plus c, that's great. If you can just jump to that in your head, that's really the level I want you at. But if you can't do that, you could always do it this way and say that's an e to the u times a du over 3, which is a 1/3 the integral of e to the u du, which is a 1/3 e to the u plus c, and then you could jump to the answer. All right, so that's the end of the very straightforward ones where I'm not asking you to compare two very similar integrands and figure out what differences the similarities make. So let's look at P5. We're going to integrate both A and B, and I want you to look at the subtle differences. So in A, I have to use U-sub because in A, I can't distribute this x, right? So I have a function inside a function, right? The x minus 7 is inside a root. I have a du that is a dx. So I'm going to have to use U-sub, right? There's nothing I can do here. I can't distribute. I'm going to have this x root u times a du, and then I'm going to have to use this formula like we've seen before. I'm going to solve and get u plus 7 is my x, and I'm going to have to replace this with a u plus 7. Notice that now I'm able to distribute this, and I'm going to get that this is a u to the 3 halves plus a 7u to the 1 half du, and now I can integrate. So I'm going to up the power by 1 and get u to the 5 halves, and then times by 2/5, because that's the same as dividing by 5 halves. I'm going to up the power by 1 and get u to the 3 halves, right? And then I'm going to times by 2/3, which will give me a 14/3, right? Plus c. And then my last step is to replace what u is, which was an x minus 7 to the 5 halves plus 14/3 x minus 7 to the 3 halves plus c. So there's my answer. Now that's the harder of these two, okay? So what I want you to notice is because the x minus 7 was inside that root, that's what I had to do. But here, look, this one I can just distribute. This is an x to the 1 half times an x minus 7. I can just distribute, right? So I'm going to get that this is an x to the 3 halves minus a 7x to the 1 half, right? So I just use some algebra and I distribute, and now I can do the power rule. So I'm going to get a 2/5 x to the 5 halves minus a 14/3 x to the 3 halves, right? Because it would be times 2/3 plus c. And that was much faster, right? So notice that subtle difference about whether the x minus 7 was inside the root or outside of the root, right? Huge difference. All right. Okay, so now the only difference here is that this one has an x and this one doesn't. This is going to be U-sub, and this is going to be an arctan. So if I try making u the entire inside of the bottom, my du is going to have a 2x dx, which is a multiple of 3x. I get that it doesn't look like a multiple of 3x because it's a fraction and you're not going to like it, but the x's will cancel. So I get that this is a 3x over u times a du over 2x. The x's cancel, and I get that this is a 3 halves times the integral of du over u. So that is going to be 3 halves, the natural log of the absolute value of u plus c, which is 3 halves, the natural log. And then I don't actually need the absolute value because x squared plus 4 is always positive, right? A sum of squares is always positive. It's not wrong if you keep the absolute value, but you don't need it in this case. So that one, right, that was U-sub, right? But when it's not a 3x on the top, when it's just a 3 on the top, I now need to use an arctan. So I know the bottom's not u, but I say, oh look, I can make this a squared is 4, so a is 2. Here my u squared is x squared, so u is x, which also means du is dx. So I can replace this whole integral with 3 over a squared plus u squared, it doesn't really matter, du. Well, that's a 3 times 1 over a arctan of u over a plus c. So that's going to be a 3 over 2 arctan of x over 2 plus c. So notice the only difference between these two was this little x on the top. That's the only difference, and the method was very, very different as a result. All right, so first thing I should look at is, does one of these work as U-sub, right? Well, I look at A, and I say, if I made u the entire denominator, my du would be a 2x plus 6, which is definitely a multiple, right? That's a multiple of x plus 3. I'm going to be able to cancel that x plus 3, right? So du over 2x plus 3 in parentheses equals dx. This one is definitely U-sub. So I'm going to say, cool, that's going to be a x plus 3 on the top over u times a du over 2 times the x plus 3. X plus 3's cancel. I get that this is a 1/2 times a natural log. So 1/2 the natural log of the absolute value of u plus c. My final answer will be 1/2 the natural log of the absolute value of x squared plus 6x, I think it's plus a 10, but we'll go back up to check, plus 10, all plus c. Okay, so, yep, all right, so that's my answer. Now, for the other one, when you get to ignore that. When you get to BC Calc, right, for the other one, you sometimes have to worry about a thing called partial fractions, but number one, this isn't a BC problem, and number two, the bottom doesn't factor. So the only other possibility is maybe if I complete the square, it might be an arctan. And I kind of have to go out on a limb and try that. Now, I am going to point out that some of you might be a little bit better at this as you go, at recognizing that x squared plus 6x plus 9 is a perfect square trinomial, and you could write this x squared plus 6x plus 10 as that perfect square plus 1. So some of you might be able to kind of logic through how this is actually this already, and that's great. If you can't, you're going to complete the square. So let's do a little bit of work. Okay, so if you can jump right to this, that's great. If you can't, the way you get there is you ignore the constant, you factor out the a, which is a 1, and you do that triangle step. So you divide by 2 and get a plus 3, and then square it. So you added 9, 1 times 9, you subtract 9, and you're going to get that this is an x plus 3 quantity squared plus a 1, which is the same spot I mentioned that you might have gotten to a little bit earlier. Once you recognize that, this is the integral of a 2 over, and it doesn't matter which one you put in front. You can put the 1 squared at front if you like the a squared better. It doesn't matter if you put a squared or u squared in the front. It just matters that you recognize that a is the constant. So u is x plus 3, which means du is just dx. So this is a 2 times this a squared plus u squared with a du. This thing is a 2 over a arctan u over a plus c, which means this thing becomes a 2 arctan of u over a, which is just an x plus 3 over 1, plus c. So again, so this was all on this side, right, if we make sure that's split up. So very different techniques, just from one subtle difference, right? The only difference is that this one had this x plus 3 on the top and this one has a 2. I don't know why I didn't make this one a 3 also. That would have made more sense because then they're really the same thing, but it's cool. All right. Okay, so notice the difference here. This one has an x on the top, this one doesn't. One of these is u sub and one of them is arc trig. If I try making my u, so let's try u sub on this one. If I try making my u the inside function, my du is a negative 2x dx, which is going to allow that x on the top to cancel. So this is u sub, right? So if I do this, I'm going to get that this is an x over root u times du over this negative 2x. The x's cancel. I get that this is a negative 1/2 the integral of a u to the negative 1/2. So I'm going to up the power by 1, which will be a u to the 1/2, and multiply by 2, because that's the same as dividing by a half, plus c. So I'm going to get that this is the negative square root of u plus c. My answer is the negative square root of 9 minus x squared plus c. Or you could leave it as a 1/2 power instead of a square root. I don't care. So that one's u sub, right? But this one, this is going to be an arc sine. So my a squared is 9, which means a is 3. My u squared is x squared, so both u is x and du is conveniently dx. So I'm going to get that this is the integral of 1 over root a squared minus u squared du, right? Well, that's absolutely just the formula for arc sine, like it's the exact formula. So arc sine of u over a plus c. So in this situation, this is going to give me the arc sine of x over 3 plus c, right? So again, one minor difference, the x on the top versus the 1 on the top decides entirely about whether we're talking about arc trig or u sub. All right, so that should be it for our AB video. You can take off if you're an AB student, and BC folks, hang around because we're going to do a couple more problems. All right, so we've seen examples like this before, right? One of these is u sub and one of them's parts. So here, right, the reason that this one is parts is because my inside function is just an x. It's not going to help me to make that u. But this one is going to be u sub, because if I made my u x squared, my du magically appears in my integral, right? So 2x dx. I get, and again, if you want, you can solve this. If you can just spot that it appears, that's fine too. you're going to end up getting that this is an e to the u du with a 1/2 out in front. Oh, no, not a 1/2, my bad. Because there was a 2 in the problem. I forgot I put a 2 in the problem. Right, so just to show you where that mishap happened in my brain, if I plug this in, I get a 2x e to the u times a du over 2x. The 2x's cancel. I forgot that there was a 2x in the original problem. So I get that it's just e to the u du, which integrates to e to the u plus c. This answer is e to the x squared plus c. So no BC scale needed, right? That's an AB scale. This one's parts, right? So I use Liat to pick my u, right? I say, okay, so u must be the algebraic function. And then if I want, I can use the shortcut here because conveniently my u derives away to 0. So I'm deriving a 2x to get a 2 to get a 0. What I'm going to be integrating is the e to the x, which is also super convenient because it just integrates to e to the x. I'm going to get a plus and then a minus. So my answer is going to be 2x e to the x minus 2 e to the x plus c. All right. Okay, so one of these is u-sub and one of them is parts. So we've already established, hopefully you recall, that, that natural log of x can only be integrated using parts, where my u has to be natural log, and that makes my dv dx. So u is natural log, dv is just dx. My du is 1 over x dx, which makes my v just an x. When we do uv, so this is going to equal uv, which is x natural log of x, minus the integral. When you do v du, you just get a 1 dx because the x and the 1 over x cancel. So you end up getting that this is x natural log of x minus an x plus a c. So that's parts. And that's great. This one is u-sub. The problem is that the only possible candidates is ux. No, that never helps, right? It never helps to make ux unless you're talking about arc-trig, right? And you have a u and an a. So u can't be x. So is u natural log? And the answer to that is absolutely it is. So if you make u natural log, your du is a 1 over x dx, which totally appears in this integral because there's that dx with the x in the bottom. So if you solve for dx, you get an x du. That means that we're going to get that this is the integral of u over x times x du. These cancel, and I get that this is the integral of u du. So that's a u squared over 2 plus c, and my answer is natural log of x, quantity squared, over 2 plus c. So again, subtle difference. This one's just a natural log. This one was a natural log of x over an x. One of them is u-sub and one of them is parts. All right, so one of these is probably partial fractions because the denominator factors. But if we look here, what would happen if we try u-sub, right? Well, so this one's definitely not u-sub because the top is just a 2 and that's not the derivative of the bottom. But if I try making u x squared plus, or x cubed plus x, my du would be a 3x squared plus 1, which is absolutely a multiple of 6x squared plus 2. So du over a 3x squared plus 1 is going to be my dx. Well, that means that my integral is going to be this 2 times a 3x squared plus 1, because that's absolutely what a 6x squared plus 2 is, over u, times a du over, oh, hey, look how convenient that is. There's that 3x squared plus 1 again. Oh, look, this is a 2 times a simple natural log integral. So I get 2 natural log of the absolute value of u plus c, which means that the answer I'm going to get is 2 natural log of the absolute value of, it was x cubed plus x, I'm pretty sure, plus c, but we'll go back up and double check. Yeah. All right, so that one, definitely u-sub. That means this one is really likely to be partial fractions, right? It's really likely to be partial fractions decomposition because the denominator factors. So I'm going to go ahead and do my work for my partial fractions decomposition. I get a 2 over an x times the quantity x squared plus 1 equals a over x, because that's a linear factor, plus bx plus c over the x squared plus 1, right? So I'm going to get that this 2 is a times the factor it's missing, which is the x squared plus 1, right? Plus this quantity, bx plus c times the x, right? The factor it's missing. Now, clever substitution only gets me so far here because you'll notice that 0 will knock out both the b and the c, and that there's no, it knocks it out here and here. So what I'm going to suggest is that you don't do clever sub here. I'm going to suggest it's easier to to do ax squared plus a plus bx squared plus cx, right? And then do the thing where we recognize that the left-hand side has to equal the right-hand side. So whatever x squareds I have on the left-hand side, which are none, have to equal the x squareds on the right-hand side, which are a plus b. Whatever x's I have on the left-hand side, which are also none, have to equal the x's on the right-hand side, so that means c is 0. And then lastly, whatever numbers I have on the left-hand side, which is 2, have to equal the numbers on the right-hand side. So now I know a is 2, which means I can back substitute in to get that b is a negative 2, right? Because a plus b should be 0. So I know a, b, and c. So I'm still not done with the calc, right? That's just the decomposition. So let's go ahead and give ourselves a little space down here, right? So this was the whole first method. So this is b that we're doing right here. We're integrating a 2 over this x cubed plus x dx. And we've now established that if we split this up, c is 0 and b is negative 2. So we get 2 over x plus this negative 2x over an x squared plus 1 with respect to x, right? And then c was 0, so there's no c. Okay, so this one is going to be a simple natural log, and this one's going to be u sub, but is also basically going to be a simple natural log, right? Because if this one, if I had an x squared plus 1, my du would be a 2x dx. So basically it's this exact thing but without the negative. So this is going to integrate to a 2 natural log of the absolute value of x, right? Minus, this will be the natural log of the absolute value of the x squared plus 1 plus c. And that's fine. You don't need the absolute value on this one if you don't want it, because x squared plus 1 is always positive. You do need it on the x over here, right? And that's kind of the gist. And if you did need the u sub here, right, this would end up being a negative 2x over u times a du over 2x, and you can see how those cancel. So that's how I got the negative 1 times this natural log, right? That's how I got this thing right here. All right, so again, notice the difference, right? The only difference that we had here was that this had this 6x squared and this only had a 2, and that was our difference. All right, P12. So again, we have a denominator that factors, right? So x squared plus 7x plus 10 is definitely going to factor. It's going to be an x plus 2 and an x plus 5. So realistically, one of these is probably partial fractions, and one of them is probably u sub. So I'm pretty sure that this one's u sub. And the reason I say that is because if I make my u the entire denominator, my du is conveniently a 2x plus 7, which is exactly the top. So this thing is just a du over u, meaning it's going to be the natural log of the absolute value of u plus c. So my answer is the natural log of the absolute value of x squared plus 7x plus 10 plus c. And you do need the absolute value because remember, we saw in previous problems, so x squared plus 1, x squared plus 1 is always positive because you can actually picture that. Here's 1. This is what x squared plus 1 looks like. It's always positive. But x squared plus 7x plus 10 is not always positive. In fact, it's got zeros at negative 2 and negative 5. So just don't be all willy-nilly about throwing out those absolute values, right? Keep the absolute value there unless you're sure that you don't need it. Now this one's probably partial fractions, right? Because it factors, and the top is definitely not a multiple of the bottom. So I'm going to go ahead and do my partial fraction work. Right, I'm going to recognize that x plus 14 over this x plus 2 times x plus 7 is a over x plus 2 plus b over x plus 7, meaning that the x plus, or the a is missing the x plus 7, right, as a factor, and the b is missing the x plus 2. So now clever substitution is a great call here because I have two very different factors. So let's start with the negative 7. I'm going to get 7 equals nothing where a is, and then plus b times a negative 5. And admittedly, that's not super fun, but you're going to survive. You're going to get that b is a 7 over negative 5, or a negative 7 fifths. And I get that that's not awesome, but you'll survive. When I plug in x is negative 2, right, I'm going to end up getting a 12 on this side, and on the other side, I'm going to get an a times 5 plus nothing. So I'm going to get that a is a 12 fifths. And again, that's not super fun, but you'll survive. So that means that if we jump down here to do part b again, I have the integral of x plus 14 over this x plus 2, x plus 7, right? And we get that that's going to be the integral of a 12 fifths, that's over x plus 2, plus a negative 7 fifths over an x plus 7. And basically, these are just both going to be natural logs, right? It doesn't matter that it's an ugly coefficient. And because du is just going to be dx, I can essentially do the very simple version of u sub here and get that this is the natural log of x plus 2 minus a 7/5 the natural log of x plus 7. Both of the natural logs have absolute values on the inside, plus c. And that's it. So again, not short, but just want to show you the subtle difference about those two numerators, right? They're both binomial numerators, but one of them was much easier than the other. One of them was AB and the other one is BC. Also, as a reminder, the BC exam does have AB material, so you can't just magically forget how to do the AB stuff. All right. So we have two more. Let's do P13 and P14 and then call it a day. All right, so let's look at these, right? So for this one, right, I'm likely going to be able to just do simple u sub, right? Because if I were to call u x plus 3, my du is just dx, right? So this is probably u sub, right? Because what's going to happen is I'm going to get that this is the integral of a -2 u to the -2nd du, right? So I up the power by 1 and divide by the new power. So I'm just going to get that this is a 2 over u plus c, which means we're going to get 2 over x plus 3, all plus a c. Great, simple u sub. The other one is probably partial fractions, right? So this one is likely partial fractions, right? So I'm going to go ahead and do my partial fractions work. I'm going to say 5x minus 2 over an x plus 3 quantity squared equals a over x plus 3 plus b over x plus 3 quantity squared, right? So when I get my common denominator, the big thing to notice is that b doesn't need to be multiplied by anything, right? So there's actually a couple of ways to do this. You might find that this is one that's easier to do by just distributing, right? You could do clever substitution, that's absolutely fine. But if you chose to do the distribution method where you say that the x's have to equal the x's and the numbers have to equal the numbers, that's actually pretty straightforward here because the left-hand side, right, the x's have to equal the x's on the other side, right? Well, the only x on the left-hand side is a 5, and the only x on the right-hand side is an a, so you can just say a is 5, right? For the numbers, -2 on the left-hand side has to equal 3a plus b. Well, you know what a is, right? So that's -2 equals 15 plus b. So you get a -17 for your b. So there's your a and your b, right? Once you know that, now we just have to actually do the calculus. So let's go ahead and finish b down out here, right? So we were integrating 5x minus 2 over this x plus 3 quantity squared. And we established that it's going to be a 5 over the x plus 3, which is just going to be a simple natural log, right? And a -17 over the x plus 3 quantity squared dx. So essentially, this one is a simple natural log, and this one, right? So this one's a simple natural log, and this one was basically the same problem we did in part A, just with a different number on top instead of a 2. So if we made u x plus 3, right? What's going to happen is we're essentially integrating 5 over u du, right? Plus this is a -17 u to the -2nd du, right? So du would just be dx. So we end up getting that this is a 5 natural log of the absolute value of u, right? And then when we up the power by 1, it's going to be a -1 and divided by the new power, so we're going to get a plus 17 x plus 3 to the -1st plus c, and that's fine, although you're more likely to see it with the x plus 3 on the bottom, right? You're more likely to see it like this. So again, notice that the BC scales and the AB scales overlap a lot, right? To finish out B, even though B was clearly a BC level problem, you still had to do the same scale as an A, just with a different part of your more complicated integral. All right, so last problem, and then we're going to call it for this unit and this video. So again, probably partial fractions on one of them because the bottom's already factored for you. So the trick here is I don't think I can do simple u sub. It's not going to help me to make the bottom u, but I happen to notice that this one factors. And I say, wait a second, maybe I could use some algebra to factor first. And look what's going to happen to the x squared plus 4. This is a bit of a trick problem because if you don't see it, you're kind of in trouble. So this one is going to integrate as either really simple u sub, or you can just kind of figure it out because du is equal to dx. 3 natural log of x minus 1 in the absolute value plus c, right? Okay, so that's b. And it's pretty likely that a is partial fractions, right? And it's probably fairly ugly because they did the work to factor it for you, which is never really a good sign. So when I go ahead and do my partial fractions work, I'm going to get that this x squared plus x minus 17 over this disgusting thing, and I usually like to put the linear one first, but that's fine, is a over the x minus 1 plus a quadratic factor has a linear numerator, so bx plus c over the x squared plus 4. When I clean this up to get the same denominator so I can set the numerators equal, the a is missing the x squared plus 4, right? The entire bx plus c is missing the x minus 1. So I'm going to go ahead and do clever sub. I can use x equals 1 to quickly find a, because x equals 1 will knock out the entire second set. So I'm going to get 1 plus 1 minus 17 equals a times 5, right? That's a negative 15 equals 5a. So a is a negative 3, and that's great. I can use x equals 0 to knock out the b, which will allow me to find c, since I already know a. So when I use 0, I'm going to get a negative 17 equals a times 4, right? Plus the b is gone, plus c, and I was plugging in 0, so that's a negative 1. So I get negative 17 equals negative 12 minus c. I add the 12 over, I get negative 5 equals negative c, so c is 5. Now that I know a and c, I can pick literally any easy number to find b. I'm going to pick 2 because I always think 2 is the easiest other option. So I'm going to pick 2. That's going to be 4 plus 2 minus 17. On the other side, I'm going to get my a times an 8 plus 2b plus c times a 1. So that's going to end up giving me a negative 11 equals negative 24 plus 2b plus 5. So I get negative 11 equals negative 19 plus 2b. I add the 19 over and get 8 is 2b, so b is 4. Okay, so after all that work, because that was not a small amount of work, right, we're now going to have to establish that my original integral, so we're still working through a, right, the integral was x squared plus x minus 17 over this entire ugly monstrosity. We can double check in a second. And we now know that it's a, which was negative 3 over the x minus 1, plus b, which was 4x, plus c, which is 5, over this thing. Well, so after all that, I'm going to have to split this into 2, and we've seen that before. So this is about as awful as I can get. So I'm going to split this into 2. I'm going to get that this is the integral of a negative 3 over x minus 1, right? Plus the integral of a 4x over x squared plus 4 dx. That's going to be, so this is going to technically be u sub. This is going to be u sub. Plus a 5 over the x squared plus 4 dx, and that's going to be an arctan, right? So this one is going to be a negative 3, the natural log of the absolute value of x minus 1. This one, your u is x squared plus 4, so your du is a 2x dx, which means you're going to end up with a 2 in front of this, because when you clean this up, the 4x and the 2x are going to cancel, giving you a 2. So you're going to end up getting a 2 natural log of the x squared plus 4 inside the absolute value. Again, you don't technically need it. And this one's an arctan where your a is 2 and your u is x. So you're going to get that this is plus 5 over a arctan of u over a plus c, and that's your answer. Again, you could not, if you want, you could take the absolute value off this one because x squared plus 4 is always positive. So you can see how much work subtle differences make, right? So look at the difference between these two numerators. For this one, I was able to do the problem almost instantly. For the BC version, it took a lot of space. So hopefully this was helpful, and that is the end of Unit 6.